So we can now turn waste, like old tires, into a fuel called pyrolysis oil. Pretty amazing, right? But here's the catch. In its raw form, this stuff is, well, it's unstable, it's corrosive, and it's basically unusable. So how do you clean it up? Today, we're going to dig into a strategy called Good Enough that's all about prioritizing profit over perfection, turning a hazardous waste into a valuable product without completely breaking the bank. And that really brings us to a fundamental business question. When you're making a product from waste, is your goal always perfection? Like creating a pristine road-grade diesel. Or is there a smarter, more profitable path where good enough is actually the winning strategy? Okay, here's the choice producers are facing, and honestly, it all comes down to cost. On one hand, you've got mild upgrading, doing just enough to make the oil safe and stable. We're talking maybe $10 to $30 per ton. But what if you aim for deep refining, for that perfect road fuel? Well, that cost just skyrockets to between 100 and 200 bucks a ton. This huge price gap is exactly where our entire strategy is built. All right, so let's walk through this whole good enough approach. First, we'll break down the strategy itself. Then, we're going to dive into the 3 essential jobs you have to do: stabilizing the fuel, neutralizing those nasty acids, and cutting out the sulfur. And finally, we'll see how all these steps come together to create the final product, a really valuable marine fuel. So let's start with the strategy. Here's the thing. Not every engine out there needs pristine, perfect fuel. Think about massive markets like the global shipping industry. Their engines are absolute workhorses that can handle something less than perfect. For them, it's not about purity, it's all about reliability and safety. This is what we call the low-hanging fruit. And this quote just captures the mindset perfectly. The goal isn't to get rid of every single impurity. No, it's to solve the most immediate dangers first. Stopping sludge from clogging up the tanks, preventing acid from eating through the pipes, and making sure the fuel won't just easily catch fire. It's about tackling the biggest risks right up front. Okay, first job up, making the fuel stable. Raw pyrolysis oil is chemically reactive. What that means is, over time, it just degrades and forms this thick sludge that would absolutely destroy an engine. The solution is a process called hydrotreating, and it tackles the problem right at the molecular level. So what's the actual culprit here? It's these molecules called olefins. You can see they have a carbon-carbon double bond. Now, think of that double bond as kind of like a pair of hands reaching out, just ready to grab onto other olefin molecules. And when they link up, they create these long, sticky chains, and that's the sludge we're trying to prevent. The solution, as you see here, is actually surprisingly elegant. You take that reactive olefin and you add some hydrogen gas with the catalyst. The hydrogen basically caps those reaching hands, breaking one of the double bonds. And just like that, you've transformed the unstable molecule into a stable one called a paraffin. Problem solved. Now, this is crucial. This process doesn't need extreme conditions. The temperatures and pressures you see here are considered low severity in the refining world. And that's key, because low severity means lower energy use and less expensive equipment, which, you guessed it, directly supports our low-cost strategy. And hey, to put that 30 to 50 bar number into context for you, that's about the same pressure you'd find inside a standard scuba tank. In a world where high-pressure refineries can run at 200 bar, this is a relatively gentle process, one that definitely doesn't require a billion-dollar facility to pull off. But it's really important to understand the limits here. This low-severity process is basically a band-aid for stability. It fixes that olefin problem, for sure, but it does not remove the other major contaminants like sulfur or nitrogen. For that, you'd need much higher severity and a much higher cost. This is a targeted fix, not some cure-all. Okay, with the oil stabilized, we've got to face our second job: neutralizing acid. This is especially critical for oils that are made from biomass. They are so corrosive they can literally eat right through steel pipes. This threat absolutely, positively has to be neutralized. So just how acidic are we talking? Well, the total acid number, or TAN, can be over 50. To give you some perspective, a standard fuel might have a TAN limit of less than 0.5. So a value of 50 is it's devastatingly corrosive. You simply cannot put this stuff in a normal fuel system without completely destroying it. The solution is a really neat bit of chemistry called esterification. You take the corrosive organic acids in the bio-oil and you react them with a simple alcohol, something like methanol. The reaction creates two things: a neutral, non-corrosive molecule called an ester, and water. You've effectively neutralized the threat. It's that simple. All right, our third and final job targets a problem that's really specific to tire-derived oil, sulfur. You see, sulfur is added to make tire rubber durable, but it ends up contaminating the oil during pyrolysis. And if you want to sell this as a marine fuel, that sulfur has to be drastically reduced to meet some very strict global regulations. And here it is. This is the hard number that drives everything. The International Maritime Organization, or IMO, says that all fuel used in open seas must have less than 0.50% sulfur. Raw tire pyrolysis oil, it's typically got 1 to 1.5% sulfur, so it fails this test right out of the gate. Desulfurization isn't optional, it is absolutely mandatory. So producers face another choice. They can go with hydrodesulfurization, or HDS, which is the industry standard that uses hydrogen. It's proven, it's reliable. Or they can opt for something called oxidative desulfurization, ODS, which avoids the expense of hydrogen but adds some process complexity. It's a classic business trade-off, right? Do you invest more capital upfront for a simpler process, or save on capital but have to manage a more complicated one? So, after we've done those three big jobs, stabilizing, neutralizing, and desulfurizing, what do we actually have? Well, we've taken a raw, really problematic waste oil and we've crafted it into a valuable, market-compliant product. Let's take a look at the final result. But before the oil is truly ready, there's one final critical safety step. Marine fuel has to have a flash point above 60 degrees Celsius to prevent fires at sea. Raw oil often fails this test, so the most volatile bits are stripped out. This crucial step not only makes the fuel safe, but it also creates a valuable co-product called naphtha. Win-win. And this report card right here tells the whole story. Just look at the transformation. Stability goes from poor to good. Sulfur drops from over 1% all the way down into the 0.3 to 0.5% range, meeting that global spec. For biooils, the acid number just plummets, and the flash point is raised to be safely above that 60-degree limit. The oil is now on spec and ready to be sold. So let's just recap the power of this mild upgrading strategy. It solves the critical stability problem, it neutralizes the corrosive acids, it meets that all-important sulfur cap for marine fuel, it makes sure the final product is safe to handle, and most importantly, it does all of this while avoiding the absolutely astronomical costs of deep refining. Now look, this strategy isn't for everyone, but it is a brilliant fit for early-stage projects that have to minimize those initial costs just to get to revenue. It's also perfect for producers working with really difficult feedstocks, like tires or biomass, where aiming for that perfect road fuel quality is often just way too expensive to be profitable. And that really leaves us with a final thought to chew on. In the world of new circular economy technologies, where cost is literally everything, maybe the most intelligent strategy isn't chasing some imaginary ideal of perfection. Maybe the smartest path to making a real impact is creating a product that is simply good enough to solve a real problem in a massive market today.